All right. So here what we're going to do is we're going to start looking at chapter 3, section 1. And here what we're going to see is graphing quadratic functions. Okay? That's what we're going to see. We're going to graph quadratic functions. Namely, just as a reminder, a quadratic function, that's a function that can be written this way. That can be written this way here. We have ax squared plus bx plus c. And this is where a, b, and c, those are numbers with a not equal to 0. If a were 0, though, then you would just have a line, bx plus c. Excuse me, but, we did that already. That's what the quadratic function is. The graph of it that we're going to graph, it's called a parabola. I mean, of course, the graph will depend on a, b, and c. And it's called a parabola, in fact, no matter what. The domain, what's nice about these functions is the domain doesn't change. The range will change. The range will depend on a, b, and c. But the domain is always the same. The domain is always all real numbers. That's what this is telling you. All real numbers. So the range will depend on a, b, and c, though, but the domain is always the same. We have that. I mean, you'll see. So I just threw in some examples here just to help illustrate what's going on. So for instance, this is the graph of y equals x squared plus 1. Here we have negative x squared plus 1. Here, notice that a is actually 1. A is the leading coefficient. If a is not written out explicitly, then it's understood to be 1. We have seen that before with polynomials. And this is what the graph actually looks like. I mean, I think we've seen y equals x squared before. You can see the graph looks very similar to that. In fact, the graph of any quadratic function is going to look similar to this, or it'll look similar to this. In this case, your a is negative, namely -1, and the graph is pointing down, so to say. What might happen is it might be shifted horizontally or maybe vertically shifted up or down more. Or it could be, how do I say it? It could be horizontally compressed or horizontally stretched. That can happen also, but it's going to look something like one of these two. The general shape of it, that is. In this case, notice that the graph keeps on going up forever. The graph keeps on going up. In fact, you can actually get the range if you think about what we did in 2.4. In 2.4, namely what we do, remember what you do is you could draw these horizontal lines from the graph to the y-axis. And from there, you can figure out what the range is. I mean, if you were to do this, hopefully you get the idea that every number from the vertex on the y-axis, in this case upward, like so, that's going to be the range. So the range is going to be everything from this point down here upward. Whereas here, same idea, except it's pointing down. Right? So if we draw some of those horizontal lines to help us, hopefully you can see that, well, yeah, you can see that the range is going to be everything from up this top all the way down to minus infinity. Keeps on going. So you do get intervals for the range. One case, it's going to go from something to infinity. The other case, it's going to go from minus infinity to a number. The domain never changes. Just going to say that. Oh, we have that. Also, if you notice, it might be kind of hard to see it, especially since I drew these lines. If you would imagine taking this graph and folding it along the y-axis, both halves of the graph would line up. Both halves of this graph here would line up, overlap each other. You could also think of the y-axis as almost like a mirror, and the graph you're reflecting about it. Because of that, we say the y-axis in this case is the axis of symmetry. So every parabola, in other words, has what's called an axis of symmetry. And the idea is if you fold the graph along the axis of symmetry, which is always the vertical line, both halves of the graph will match up. So we have that. So if A is positive, we're going to get this kind of graph. It's going to open upward. Excuse me. Whereas A is negative, it opens downward like this. Okay? As you can see. So if A is positive, it's going to look something like this. If A is negative, it's going to look something like this. The arrows may not be drawn, but it's understood the graph keeps on going. Not only that, you can see from these two, from what I drew, and even from the previous two graphs, there was some point where the graph turns around. Go back to it. You know, you can imagine walking along the graph like you're walking along a trail. And on this graph, there's a point where once you get to the bottom, so to say, you turn around and walk the other way. Same thing over here, right? You're walking along the path, okay? You reach a point, and then you turn around and go the other way, like so. Okay? These points, this low and high point here, this low point here and this high point here, we call those the vertex. That's the vertex of the parabola. That's what the vertex is. That's the point where the graph turns around. And the vertex is actually very important. You actually need it to graph the parabola. And what's nice is there are formulas for it, as we'll see. You know, there are formulas for it. And that axis of symmetry, what I mentioned before, this goes a little more into it. It's always the vertical line through the vertex. I mean, in this case, the axis of symmetry happened to be the y-axis. It doesn't have to be, though. It's the vertical line through the vertex. That's just what it is by definition. And the idea is, you can imagine, maybe better with this graph, taking the graph, folding it along the y-axis, or the axis of symmetry in this case. Yeah. And what happens is both halves of the graph would line up. I mean, I don't know if I know I haven't gone over what it means to be symmetric about something, but you could think of it as being symmetric about the axis of symmetry. So we have that idea. Okay. Now, we saw now in the definition, let me go back to it. Here we have one way of writing a quadratic function. You know, this is one way of writing it out. There is another way, which is also useful, called the standard form. And that's what this is. So the standard form is when you have this. This A is the leading coefficient. We also have this H and K. And what are H and K? Well, it turns out the point, HK, is the vertex of the parabola. So right away here, if you happen to have this form, you can get the vertex of the parabola very easily, actually. If you had the other form, the vertex is not as obvious, but it can be calculated. And you can actually go from one form to the other. Namely, let me show you the next slide. Namely, go from here. This is what we started with in the definition. I'll get to the other stuff. If we go from here to here, as you can see, we would just use a process called completing the square. I haven't gone over that. Hold on, let me just see my recording. I have not gone over that process. I do cover it in the book. It's just for time consideration. I think it's better to skip it. You can actually go from this form to this form by completing the square. It is a nice process. It's a little tedious, but it's useful. But to go from this form, the standard form, to this form, that part's easy. You just FOIL. That's all you have to do there. Now, if you know about vertical and horizontal translations, you could use this to graph the parabola. Again, I didn't go over that, so I'm not going to go into that. But what's nice is here, you can get the vertex, though. We have these formulas, it turns out. Namely, if you happen to have this form of the quadratic function, the vertex is just this here. So you would have to calculate negative b over 2 times a, and then do f of that. It also tells you how to another way to get from this form to the standard form. Namely, this would be your hk, so your h would be minus b over 2a. To get k, you just do f of h. Now you might be thinking, why do we care if we have just this form and the formulas? This form does have uses. It does give us another way to determine the x-intercepts of a quadratic function, although I didn't go over the method using this. But there is that other method. Also, what's nice about this form is, if you happen to know ahead of time what the vertex has to be, either someone told you or you read it from a graph, and you know another point the graph passes through, or another point that the graph passes through, you can easily get a formula for the quadratic function using this. This one you could also it would take more work though. Here you could do this though. We won't do that kind of example today, but Friday I expect to. Okay, let me pause the recording.